we're going to wrap up this chapter today. We might even move into the next chapter if we have time. And we're going to have the test on Thursday, and that's all that we'll do. It'll be 50 questions-ish, just like last time, but just 50 this time. So you only have to use one side of the Scantron. True and false? Every question. All right, you will see some of those questions that you've been seeing in class, like, a handful of those just outright. So make sure you at least get those right. Make sure you review over those. I sent them out as a PDF earlier. And we'll do a few more today in class. Let's see, where did we leave off? That was a rhetorical question. I'm sorry. I'm going to look at my notes. I have it. I will give you the couple of equations for the exam. Those two frequency equations, the f equals 2 pi root k over m, and that f equal 1 over TL t over mu. So, we're not actually using those with numbers, but you just have to know the relationships between the variables. If you increase one thing, what does it do to the other thing? So you need to know, how the variables respond to one another, and then also what the variables mean. So like in that 1 over 2L, the L is for the length of the string. The T over mu, T is tension, mu is a mass density, or you can just think mass if you want. And then for that 2 pi K over M, K is related to the what of a spring. Y'all remember? Stiffness, right. So a really stiff spring, like on a car, has a high K. A really loose spring, like a slinky, has a small K. It's called the spring constant. All right, so it looks like we left off with the, yeah. Just those two, right. And so you do need to know a couple of others. There's the V equals lambda F. The velocity of wave is wavelength times frequency. I don't think that there were any others, really, were there? I don't think there were, but look through your notes. When I make out the exams, I basically go through the notes and I pick out different things. There will be some identification things based on either the speech or the hearing, which we'll look at today. The parts of the ear, parts of speech, not parts of speech, but parts of the speech system or whatever, the larynx, the vocal cords, the glottis, all that business. More slides here. Any other questions about the exam? Multiple choice. Bring a Scantron. No calculators. You shouldn't need a calculator. No questions? You feel comfortable about it? Yeah? I want y'all to do well on this. I would read through the chapter, make sure that you got everything, read through the notes. The screencasts are online, or most of them are. Sometimes I've missed out, but all right. All right, so we were on the middle ear, the anatomy and physiology of hearing. Okay, looks like we were left off with the auditory ossicles. The auditory ossicles are the three smallest what in the body? Right, they're the three smallest bones in the body. I'll show you a little video in just a second on how these work, how all the various systems work together. The auditory ossicles, it's in the middle ear, right? Isn't that right? Yeah, in the middle ear. These are the three small bones in the middle ear. They have names. The first is the malleus. The second is the incus. And the third is the stapes. I think it said stapes? Is that how you pronounce it? You don't need to know these names, honestly. They're not going to be on the exam, but I just want to sort of present them to you. Most of you probably know them anyway. But the malleus, I'll show you a picture in a bit. It's called a malleus. It looks like a hammer. And it's connected to the eardrum. So when you get vibrations in the eardrum, it oscillates this malleus. And then the malleus is connected to the incus and the stapes. The incus looks like an anvil, and the stapes looks like a stirrup. Collectively, these transfer vibrations from the eardrum and you do need to know this. They transfer vibrations from the eardrum to the inner ear. All right, so that eardrum vibrates. Why? The eardrum, which is the beginning of the middle ear, why does it vibrate? It's because of sound, right? Sound, you hear sounds, and then that causes pressure waves to go through the air. They go into your, what's this called, the auricle, and down into the auditory canal, and then they impinge upon the eardrum, and they cause it to vibrate back and forth at a particular frequency, and then that causes those bones to vibrate back and forth. And then they transfer those vibrations from the eardrum to the inner ear. You actually get an increase in pressure from the eardrum to the inner ear by about a factor of 20. Right? So the pressure of the vibrations is amplified by about 20, or is increased. Is increased by about 20. And the reason they're increased, remember our definition for pressure is force over area. The reason they're increased is if we decrease this area, right? The eardrum has a large area in comparison to the bones, and so if we decrease this area, we increase our pressure. If we make A small, P goes up, and so that pressure then is increased, or rather the force is increased. But you get this sort of amplification of the vibrations. All right, and then we move into the inner ear, and the inner ear has three parts. You need to know what these three parts are and just sort of their basic functions. Just remind you, so I said with the bones, you need to know the bones and what they do. That is that they transfer vibrations, but I'm not going to ask you about the particular names or what they look like. Is that clear? Okay, but you do need to know what they do, their function. The inner ear has three parts. With the inner ear, you need to know the three parts and the function of each. You should be able to identify them as well, looking at a figure. There's a figure in your book, and I think I showed one last time. Is that right? Did I show the figure of the ear? If not, I'll show it today. So the cochlea, this is a fluid-filled chamber. It sort of looks like a snail. That has pressure waves for different pitch sounds. So in this chamber, when these sounds come into your ear, strike your eardrum, cause those bones to vibrate, those vibrations are transferred to the cochlea, and it'll set up pressure waves within the cochlea dependent upon the frequency or the pitch of the sound. And those pressure waves cause the, I don't know how to say this, basilar? Who knows this? What is it? Basilar? Okay. This causes the basilar membrane to vibrate. in different ways depending upon the pitch of the sound. On the pitch or the frequency of the sound. Remember, pitch and frequency are the same. A high pitch means a high frequency, low pitch means a low frequency. And then fibers in this membrane. I'll show you a little video in just a second. Fibers in the vascular membrane. Stimulate hair cells. That are connected to the auditory nerve. Right, so these pressure waves come into your ear canal. They vibrate your eardrum. They cause those bones to vibrate as well, and then those vibrations are transferred into the cochlea. Depending upon the frequency of the sound and the frequency of the vibrations on the eardrum and the frequency of those vibrations transferred to the cochlea, it'll set up these pressure waves within this fluid in the cochlea, right, this fluid-filled chamber. And then, depending upon those pressure waves, which have a set frequency, they will stimulate this membrane, which is connected to the hair cells, which are stimulated further. And then those hair cells actually send an electrical signal to the brain through the auditory nerve. Right? And then the auditory nerve is connected to the brain. And so it goes from there to the brain. And then your brain actually processes that electrical signal and allows you to know what sort of sound it was. What was the frequency or pitch, or what was the source of the sound? All right, so that is all in the cochlea. The primary purpose of the cochlea is to convert these vibrations into an electrical signal, which then goes to the brain via the auditory nerve, the cochlea. All right, and then that's a couple other things. These were just sort of thrown in here. These are primarily not for hearing, but they're for balance. So your inner ear has a large part to play in your balance. So I'll just sort of give them in name only, but you won't see them on the test on Thursday. And that is the vestibule and the semicircular canals. And both of these are to help you maintain balance. Both of these are for balance. I have a little video here. It's an animation of what happens inside of the ear, how you get these vibrations that vibrate the eardrum, transferring that to the bones inside your ear, those three smallest bones, and then transferring those vibrations to the cochlea, setting up pressure waves within this fluid, and then further stimulating the hair cells and sending information to the brain. So let's just watch this. All right. Let's look now at just a few hearing problems, and then we'll go into the intensity of sound. Hearing problems. All right, you can have a number of different hearing problems. One, you can just have an obstruction of the ear canal. You know, your body produces wax to keep debris sort of continually flushed out of the ear canal so that dirt doesn't build up too much in there. And that wax serves a purpose to keep it clean. Sometimes you can get too much wax, so it can just be obstructed by earwax. And like I said, you're only supposed to stick nothing smaller than your elbow, if you could even get your elbow, or maybe a friend's elbow, into your ear. So So no fingers, no Q-tips, no keys, none of that business, because it can actually impact that earwax and cause greater problems. So I had a friend, she was having some ear infections, and she read that you could put garlic in your ear, which is true, I think, that you can use garlic or garlic oil in your ear and it'll help the infections. But she instead stuck a big old piece of garlic down in her ear, and then it got stuck, and she had to go to the doctor and explain it to him that she had put this big old piece of garlic, like a big clove of garlic, stuffed down into her ear. So anyway, you can just have obstructions, earwax. You can get water, like swimmer's ear. These things are fairly minor. You can also have a perforated eardrum. That's where you actually get a tear in your eardrum. That can be more serious, either from very loud noises or other traumatic events. You can have a middle ear infection. Kids often have middle ear infections. Middle ear infection, this can cause fluid buildup. Behind the eardrum. So it can't vibrate properly. Remember we had the tube, gosh, what's it called? The eustachian tube, I think. Is that right? The tube that runs down. And if that gets clogged up, as it does, like when your sinuses are clogged up, then you can get fluid buildup behind your eardrum, and then you just won't be able to hear very well. So often when we're sick, like we feel this way, it's like you just can't hear very well because we have this fluid behind our eardrum, and it just doesn't vibrate the way that it's supposed to. And then, of course, that can be infected, and that can cause other problems. Most hearing loss, or you can have cochlear problems with the cochlea. And this is usually due to the loss of hair cells. Either through damage by very loud noises or some degenerative disease, you can lose those hair cells. Remember, the hair cells are the things that actually transmit the electronic signal to the brain. You have the sound that comes in, they vibrate that basilar membrane, and then they actually transfer that to the hair cells. And if you lose those hair cells, then that's a pretty major portion of getting sound to the brain. So this can be caused by disease, age, very loud noises, like at rock concerts or clubs or whatever. So if you all go out to clubs or concerts, you should always wear earplugs, right? Or even better protection, you should get some big ear muffs, right? Like we wear when we're using power tools, and wear those to, concerts and stuff. And then finally, the fifth thing, you can have brain injuries. So it could be that the ear is still working just fine, and it's actually transmitting a signal to the brain. The brain just isn't processing it. That reminds me of my little boy when we first moved here. We're not from here. I don't know if y'all knew this or if y'all could tell, but we moved here 8 years ago, and my boy was like 2, and we're right on the parade route, so a couple times we go out to the parades, and he didn't like the loud noise, and so he would we had some earmuffs like you wear in the wintertime. My wife's from Missouri, so she has all this winter gear. She'd bring earmuffs, and he'd wear his earmuffs out to the parades, which was further evidence to everybody that we knew that we were not from around here, because my little boy comes out with his earmuffs on for the parade. He's like 2. I mean, anything you do when you're 2 is cool looking, I guess. All right. So those are just basic hearing problems. All right. Now let's look at the intensity of sound. Actually, let's see if we have any questions. I think we had a few questions. We did this one, right? Infrasonic waves. This one. Let me reopen this. Okay. Yeah. So we have not done this one. All right, so which of these is not a part of the middle ear? All right, just a few more seconds. I'll stop at 50 seconds. All right, very good. The auricle is actually what part of your ear? Right, the big floppy thing on the outside of your head? Or some of you don't have big floppy ears, but like, I have big floppy ears. All right, and the cochlea does which of these? What's the purpose of the cochlea? Remember, I sent these questions out last week sometime, but it's good to review them because some of these questions, honestly, I just cut and pasted into the exam. Not very many, but a handful of them. All right, I'll stop at 48. 48. Okay, very good. The primary purpose of the cochlea is to send electrical signals. These other things are not things that the cochlea does. Which of these may result in hearing loss? I'll stop at 28. 28. Very good. Do y'all cover the ear in anatomy? You cover like the whole human body, huh? Basically. Oh, is that right? Yeah, D is right. Okay, we'll look now at intensities. We're going to actually look at intensity of sound and then also the intensity level of sound, the sound intensity level. And those sound very similar, but they're actually quite different. They're related, but they're different. So you'll need to know the difference between those. But first of all, you know, sound carries energy. That's true for all waves, actually. But sound in particular carries energy. And so when we're talking about sound, we need some way to describe how much energy it carries. And one of those is we're going to measure the intensity. And then later we'll talk about the intensity level, which is something different, a different way of measuring intensity or a different way of talking about it. But the intensity is just simply the power over the area. Right? Remember, power is energy per time. Energy per time, or work per time. And so this would be in the units for power were watts, and of course the units for area are meters squared. So our basic SI units for intensity are going to be watts per square meter. And if you forget the difference between intensity and intensity level, just look at the units because intensity will be in watts per meter squared. And then of course, if you've been reading ahead, the intensity level is measured in watts. This is more common when we talk about sound. The decibels, right. So intensity level will be in decibels. All right. We're going to have two reference points for this. And that's going to be the threshold of hearing and the threshold of pain. The threshold of hearing, that is the lowest, the quietest noise that you can hear, its intensity is going to be 10 to the minus 12. So I'm going to call this I naught. This is our threshold of hearing, and it's 10 to the minus 12 watts per square meter. 10 to the minus 12 watts per square meter. And then the threshold of pain has an intensity equal to 1 watt per square meter. All right, so this is sort of the range of hearing, that we can hear something from 10 to the minus 12 watts per square meter, and then safely up to 1 watt per square meter before we actually start feeling pain. And of course, that might be different for different people. Like if you've suffered hearing loss because you played in a rock band in high school or whatever, then your threshold of hearing might be greater than that. You can't hear quiet noises. Okay. Going back to, we'll come back to this and how these are important when we actually define the intensity level, the sound intensity level. One other thing about intensity, though, our intensity is equal to power over area. And so if I imagine that I have this source of sound, it's sending out sound in all directions, and then I imagine that there's a sphere around it. This sphere has an area equal to 4 pi r squared. Right? You don't need to know the equation for the area of a sphere, but you do need to know that it has this relationship with r that's squared. So the area of a sphere is proportional to r squared. And so that would tell me then that the intensity is equal to P over 4 pi r squared. This is a particular law that, or a mathematical relationship. We call it an inverse square law. Or an inverse square relationship, let's call it. And it just says that I is proportional to the inverse of r squared. So an inverse square relationship just says that I is proportional to 1 over r squared. And so that has some implications about the distance that you are from a source. So let's say, for example, you're you have a speaker, and it's putting out an intensity, or rather, it's putting out let's say this is your speaker right here. You stand a distance of 1 meter from that speaker, and you measure an intensity here at this particular point equal to, I don't know, 10 to the, I'm just going to use some round numbers, okay, just to make it easy. Say 2 watts per square meter. All right. And then if I move to 2 meters away, all right, what is my new power going to be? So what I've done here is I've increased R from 1 to 2, and so I've doubled R. And so if I double R, that means that my intensity is going to decrease by a factor of 4. And we get that sort of relationship in an inverse square relationship, that if I double R, then the intensity over here is going to decrease by that same amount. All right, so I get a 1 over 2R squared by doubling R. 2 squared is equal to 4, and so that's why I get a 1/4 over here. So if I were to move 2 meters away, my new intensity would not be 2 watts per square meter, it would be what? It would be a half, right? So it would be 2 over 4 watts per square meter, or a half of a watt per square meter. Okay? We'll see some questions about this soon. I think I had some in the questions. If I increase my distance by a certain amount, that lowers the intensity of the sound, but it's not a linear relationship. It's an inverse square relationship. So that if I double this, R, I quadruple this, or I take a 1/4 of this. All right? That's also in the book. So if you have trouble with that, look through the book, or you can come see me. We can talk about it. But you will see a question like that, like if my distance increases by a certain amount, what is my new intensity? Right? The idea being that the further you get away from an object, there's a greater drop off in the intensity because of this inverse square law. Okay, let's look at sound intensity level. This is the way that we measure sound as it impacts the human ear. It's based on a logarithmic scale. And we use it because if the intensity of sound is 10 times, or is increased by 10, by a factor of 10. So I increase the intensity, say, from 10 watts per square meter to 100 watts per square meter. A person perceives it only to be about twice as loud. You know, the human ear has a very long range or a very wide range of perceptibility in sound. It goes all the way from 10 to the minus 12 all the way up to 1. So that's like a 1 with 12 zeros in our range of intensities that we can detect with the human ear. But you can't detect these sort of small gradations within the intensity. That if we have this increase by a factor of 10, then we only actually detect a small increase in the intensity. Like we only perceive it to be slightly more loud. And so we have this logarithmic scale. This is called the sound intensity level. The equation looks like this. The intensity level, which is Li, is equal to 10 times log of I over I naught. You're not going to have to do any logarithms, but I will show you sort of what you will need to know. So if I want to compare the intensity of two sounds, or first of all, here I naught is our threshold. So I naught is equal to 10 to the minus 12. Remember, this is the quietest sound that a person can hear. And with that, if you were to actually have, if I was equal to 10 to the minus 12 watts per square meter, you would have something that looks like this. You should have seen logs some time ago, but it's probably been a lot of years, like probably maybe even high school since you've even used logs. Have y'all used logs in any of your classes? Logarithms? Maybe high school, yeah. Now, if the intensity is equal to your threshold, then your sound intensity level, which remember is different, is going to be 10 log of 10 to the minus 12 over 10 to the minus 12, or log of 1. And the log of 1 is equal to 0.1. So when we're at our threshold of hearing, which is 10 to the minus 12, our sound intensity level is going to be 1, and this is going to be in decibels. So in decibels, our minimum sound that we can hear is equal to 1 decibel, or 1 dB, we call it. Right. We can compare two sounds in this way. And again, don't be sort of put off by these equations. I just sort of want to throw them out there, and then I'll show you the relationship that I want you to understand. If I want to compare two sounds, taking this logarithmic equation, I get something that looks like this. It's 10 to the delta L over 10. All right, so 10 with an exponent of the difference in the intensity levels, the decibels, and then these are the ratio of our intensities. So really what I want you to walk away from this, you're not going to have to use these equations in any way, what I want you to walk away from this is that that if we have a change in sound, the way this scale works, this logarithmic scale, is that a change in 10 decibels results in a sound that's 10 times as intense. A change in 10 decibels in the sound intensity level of 10 decibels results in a sound that's 10 times as intense. Right. That might seem obvious to you right now, but let me show you it's a little more complicated than that. So if I had a 10 decibel difference in sound intensity level, remember, which is different from sound intensity, then it would result in an intensity that was 10 times as great. But if I had a change in sound intensity of 20 decibels, what would that correspond into the change in intensity? Would it be 20 watts per square meter difference, or 20 times as great in intensity? No, it would be what? Huh? No. If I have a change in intensity level of 10 decibels, that means that the sound is going to be 10 times as intense. So let's say that our initial intensity, I1, I'll call it, was, I don't know, 1 watts per square meter. And then I increase the sound by 10 decibels. And so the new intensity, I2, is going to be 10 watts per square meters. So it increased by a factor of 10. And then if I increased it by another 10 decibels, what's it going to be? If I increase 10 by a factor of 10, what is that? 100. Right. So if I increase it by 20 decibels, that means that I've increased the intensity by a factor of 100. All right. That means that my intensity now is equal to 100 times the original intensity. I'll call it the I1. That comes about because of the way logarithms work, that they work on this scale of 10, basically. And then if I had an increase of 30 decibels, my intensity would increase by a factor of what? 1,000, right? So if I had an increase of 30 decibels, my intensity would actually increase by a factor of 1,000. If I had 40 decibels, I would equal to what? Getting the pattern here? It's going to be 10,000. 50 decibels would be 100,000. 60 decibels increase 1,000,000, and on and on. All right, so a change in a decibel, even though you're just adding 10 to the decibels each time, is actually a multiplicative factor. You're multiplying by a factor of 10 in the intensity. So even though you're just changing a small amount in the decibels, that it's actually changing the intensity by a lot. And that goes back to the way that we hear sound, that we're not able to discern between very small changes in intensity, but we can discern very small changes in intensity level because it's on a different scale. Leila, do you have a question? Mm-hmm. Is that right? I'll have to look at that and see. I think it's 0. Okay, I'll get back to it. I'll send a message out. Let me make a note to myself. All right. We clear on this, though, the decibels and how this works? That a change in decibels an increase in 10 in the decibels actually causes a multiplying of 10 in the intensity. So if I add 10 to my decibels, I multiply the intensity by a factor of 10. And that's sort of the takeaway that I want you to take here. That comes about here, right? That if I have two intensities, one twice the other, or one 10 times the other, so let's say I had 10 I1 over 1 I2, then that would mean that our delta L here would be equal to 10. Is that right? Well, never mind. That doesn't matter. But here, just remember this, that as I increase my decibels by 10, that multiplies the intensity by a factor of 10. Go with me on this? Logs can be kind of confusing sometimes, but I just want you to walk away with this idea, that as I increase the decibels by 10 each time, adding them, 20 plus 10 is 30, 30 plus 10 is 40. It increases the intensity by a factor of 10. I multiply it. Okay. Okay, so with that, now let's look at a few things regarding ear protection. You can have earplugs and a few other things. And if you're ever around very loud noises, you really should use some sort of hearing protection. Like even if you're going to a loud rock concert, you should use your earplugs or whatever kind of concert y'all go to. I'm not sure which I'll be. Is rock music? That's still a thing? No? Huh? For some people, yes. Okay, so earplugs, they just block sound from entering the ear canal. They have this rating called the noise reduction rating. Your book talks about it a little bit. This is called the NRR, the noise reduction rating. It's in decibels. So, for example, if you have a rating of 20 decibels, that means it decreases the sound intensity level by 20. This would correspond to a decrease in the intensity of 1 over 100. So if I have a negative 20 decibels, that's going to cause a decrease in the intensity of 100. And this is just like what we saw before, except we were seeing if I increase the intensity by 100, or the intensity level by 10 decibels, it increases the intensity by a factor of 10. But here we're just seeing a decrease there. It's not quite as simple as this, and your book doesn't really talk about this though, but the amount of reduction actually decreases. As the noise is louder. Right. So these earplugs, they'll work up to a certain point, but at some point, as your sound gets louder and louder, they become less effective, right? Despite what their noise reduction rating is, that reduction rating begins to tail off as the sound gets louder and louder. Another way that you can block sound, some of you might have these, noise canceling headphones. Anybody have one of these? Yeah? They work pretty well. I've never used them. Oh, really? And do you play music though through them as well? Yeah. These actually produce the sound. They have microphones and they have speakers. And so they'll detect the sound that's coming into sort of the ambient sound around you, the air conditioner or people talking or whatever. They'll detect that sound, and then they'll produce another sound that will interfere with it. So these noise-canceling headphones rely upon the phenomena of interference. We might get into this in the next chapter, because it's a property of light, but it's also it's a property of all sound, all waves. Interference. Interference occurs when I have two waves like this. I have a wave that looks like that, and then I add it to a wave that looks like this. And when I add those two waves together, I get a wave that's just flat. It cancels them out. And so that's what it means by noise-canceling headphones, that it relies upon this interference, and it actually cancels out the noise that's outside of your headphones. So for example, if our sounds are actually very complicated. Let's say the microphone detects sounds that are something like this, a waveform that looks like this, then what the headphones will attempt to do, and they can be good or bad at this, they'll attempt to produce a sound that is exactly opposite you get the idea. They'll attempt to produce a sound that's exactly opposite or exactly the inverse of the sound that it's picking up in the microphone. And then those two sounds, when they're combined in your ear, will cancel out, and you won't hear anything. But, if you add these two, depending on how good this sound that your headphones are producing, you might actually get something that's not quite zero, that has a little bit of a noise attached to it. So those are called noise-canceling headphones, and they operate on the principle of interference of waves. All right. Let's see. We're going to skip the section in your book on sound pressure level. It was just a small section. And we'll look now at noise. There's several small sections on the end of your book here. Some sounds are unwanted. Or even annoying. But others, and these are called just noise. You can also have white noise, and depending upon its frequency, it can be soothing. So there are all sorts of machines now. Like if you go over to the Dyslexia Center, they have white noise generators, white noise machines to help students as they're taking exams to sort of drown out other noises that are there. And those can be useful. Some people use these for sleeping, like on the iPod or your iPhone or whatever. They have various apps that you can buy that just generate different frequencies of white noise. And that helps some people sleep, especially if you're like in a strange place where there are lots of noises. So noise is really a subjective term. It's really dependent upon the frequency and just sort of what your particular desires are. Right? And then hearing aids. Can I go down from here? These are just sort of a collection of topics. I'll give you all just a second. Hearing aids. There are a couple different types of hearing aids. Most hearing aids just amplify the sound. So you'll have this device. It picks up sound that's coming around you, and then it'll just amplify it so that you can hear it better. Others actually select out certain frequencies, and so they'll get rid of, say, low or high frequencies depending upon your particular hearing problem, and amplify only certain frequencies. So some are selective on the frequency. Some select frequencies. And now there are actually cochlear implants, and these work a lot differently from hearing aids. If you get a problem with your cochlea, then you're actually not sending signals to the brain, and there's really no hearing aid that's going to affect that, because no matter how much sound you send into the ear, it's just not going to send that electrical signal to the brain. And so what the cochlear implant does is it detects sound that's coming into your ear, and then it transfers that into an electrical signal. So it basically does the work of the cochlea. It converts sound into an electrical signal, which then is sent directly to your brain. So they send an electric signal to the brain. Via the auditory nerve. little video here about a cochlear implant. I understand that this technology is fairly new. It's fairly complicated. It's very difficult to recreate what the human ear does, but this is sort of their last or their latest attempt at this. Right? A hearing aid simply amplifies the sound. And so if you have hearing damage, that might be enough. But the cochlear implant actually takes up issues that you might have in the cochlea, taking sound and actually generating an electrical signal and sending it to the brain. I understand, I've never had a cochlear implant, of course, but I understand that that it can take some time for the brain to actually adjust to that, because those electrical signals might be different than actually what your cochlea would send through the auditory nerve. But over time, it begins to learn that those electrical signals are actually correlated with particular sounds. So that's kind of cool and exciting for people that have hearing impairment. Okay, so one last topic here, and that is on ultrasound imaging. This will be our last topic for the chapter. Ultrasound imaging. Many of you have probably seen this or maybe even done it. It's not just for imaging. You can use it also for restorative purposes, for heating of tissue. Ultrasound imaging uses ultrasonic sound. You remember the range of frequencies for audible was from 20 hertz to 20,000 hertz. Well, ultrasound is a lot higher than that. So the range of frequencies for ultrasound imaging is 1 to 20 megahertz. And remember, a mega is a million, so that's 1 with 6 zeros, 1 million to 20 million hertz. So a much higher frequency than anything that anybody can hear, ultrasound imaging. And basically, you just have this handheld device that emits these sound waves. These ultrasonic sound waves. So if you've ever had a baby or you've been to an imaging of a baby, that's what they use in their hand. They'll put the jelly on it and then rub it all over the mother's belly. That's never happened to me, but my wife has done that. And so they just use this device and it emits these ultrasonic sound waves. Some of these are reflected back. And it measures or detects the reflected waves. And calculates penetration depth. Right. Detects the reflected waves, their travel time. Penetration depth. All right, so for example, let me try my best at drawing this. The belly button. There's a little baby in here. You have this device that is emitting waves. You know, some of the waves go here, and then they're reflected back. And they detect those waves, and they detect the time required to be reflected back. And then some of the waves might travel a further distance, and then they're reflected back. And it detects those waves and the travel time that it takes to travel through the mother's body and into the baby, and measures that travel time. And by measuring the travel time, you can determine what is this distance. So you can find what is this distance, and then you can find what is this distance. And by doing that, you can map out the image of whatever it is that you're looking at, a baby or something else in the body, right? So it calculates that penetration depth, and then you can actually construct an image. So there's actually a lot of calculations that go on in this, which is what makes computers so useful. I mean, you couldn't really do it without computers. To just do all these calculations in real time and actually construct a real-time image of whatever it is that you're looking at. You can do this not just for babies, but you can also measure blood flow with an ultrasound. Ultrasound isn't quite as good as MRI, or it's not as good as X-rays either, but it's less invasive or it's less damaging because both MRIs and X-rays can be damaging to the body, and they want to limit that as much as possible. We can calculate the resolution. The resolution of an ultrasound. When I say resolution, what I mean is the smallest possible part that it can determine in an image that it can see. The resolution is given by the wavelength, or is about equal to the wavelength. So, for example, if I have a frequency of 3 million hertz, and I have a speed of 1,500 meters per second, that's just the speed that it would travel in this particular body part or whatever in the mother's belly, then I can calculate the wavelength. Remember, V is equal to lambda times F. And so lambda, which is our wavelength of the wave, remember our wavelength is the distance from here to here on the wave. Our wavelength is just V over F. That's going to be 1,500 over 3 million. Let's see, I can cancel out that and that. 15 over 3, I get 5. So it's 0.0005 meters. All right, so that's about a half a millimeter, and that's pretty typical for an ultrasound that you have a half a millimeter resolution. That means anything that is bigger than a half a millimeter you can see, and anything that's roughly a half millimeter then you can make out in the image. That's your resolution. This is a type of echolocation. Echolocation is like what dolphins do when they send out a sound, and then they'll measure the sound that comes back that's reflected to them. Other animals do this as well. Bats do this. Bats actually use ultrasound to do echolocation. It's the same idea. They're emitting the sound, and then it comes back, and they hear it with their ears, and then they can calculate this penetration depth. They do it sort of intuitively or instinctually, but it allows them to know what's around them. They can create images in their mind of what is around them. This is just really cool, I think. This is a person. Some people are actually able to echolocate. And this is a guy, he's blind, but he can use his voice just like a bat or a dolphin to make images in his mind of things that are around him. So let's watch this. It's kind of cool. All right, we're about done. I just want to have a few more questions left over from this chapter. All right, so which of these intensities is the threshold for hearing? Which of these intensities is the threshold for hearing? Yes, we're still in another class. This is different. That's okay. Which of these intensities is the threshold for hearing? All right. I'll stop in just a few seconds at, say, 38. All right, B is right. You stand 1 meter from a sound source. If you move to 2 meters away, how much has the intensity decreased? So I'm standing 1 meter, and then I move twice that away to 2 meters. How much has the intensity decreased? Remember, this is intensity, not intensity level. All right, I'll stop at 40 seconds. 40 seconds. Okay, B is the right answer. Let me just show you. Remember, this was that inverse square law. All right, remember, our intensity is equal to P over area. That's P over 4 pi r squared. So if I increase r by a factor of 2, since it's squared, that means I'm going to decrease my intensity by a factor of 4. If I increase it by a factor of 3, I decrease the intensity by a factor of what? 9, 4, 16. It's squared. It's an inverse square. To increase a sound's intensity by a level by 20 decibels, that is, you would go from, say, 10 to 30 decibels, by how much has the intensity changed? All right, I'll stop at 40. A few more seconds. C is right. Very good. So remember, an increase in the number of decibels by 10 is a multiplicative factor of 10 in the intensity. Right. Total destructive interference of a wave results in what? I didn't call it total destructive. We just called it interference before. But total destructive is the type of interference that we talked about with the noise-canceling headphones. So if I have interference of two waves, total destructive interference, what does that result in? All right, I'll stop at, say, 42, 40, or I'll go to 45. Okay, let's see, it is B. I'll show you. You're not actually destroying the matter wave. It just goes to an intensity of 0. I understand that's a little misleading. If you saw this on the test, I would not have option C. All right, but it's actually the intensity that's going to 0. Total destructive interference is when I have two waves like this, and I add them up, and that gives me a wave with no intensity. All right, for noise-canceling headphones. So B is the right answer. By the way, constructive interference would look like this, where if I have two waves that are actually where the peaks line up with the peaks, that would give me a wave that would have a greater intensity. We might see that in the next chapter. Yeah, I think this is just a couple more. Cochlear implants do what? All right, a few more seconds, 25, I'll stop. Very good. That was a cute little girl, wasn't it, with a cochlear implant? And an ultrasound imager has a frequency of 10 megahertz, and the sound wave travels at 1,000 meters per second. What is the resolution? I'm going to help you all with this. I know y'all ready to go. V is equal to lambda times frequency, right? We want to know lambda, so that's V over the frequency. V is 1,000. 10 megahertz, that's 10 million. All right, so I can cancel out my zeros here. So that would be like 1 over 10,000. Now, we can't use calculators on the test, so make sure you can do this type of calculation. It'll be simple like this, just sort of canceling out zeros. But 1 over 10,000, let's see, this is the tens place. Well, I don't have the answer there, do I? Did I get it wrong? That's a, what's that? Yeah, it's in megahertz. So this is tens, hundreds. There should be another zero here. Answer A, please. And then y'all can go. Y'all follow, though, how to do this? No? 1 over 10,000 is 0.0001. That's our tens, hundreds, thousands. That's our 10,000s place. 1 over 10,000 is equivalent to this. What? That equation won't be on the test. You'll need to know this, but I'll have those frequency equations. The 2 pi square root of m over k, 1 over 2l, square root of t over mu. All right? Y'all have a good day. Test on Thursday. That's all we'll be doing.